Welcome to this segment of the Math Coach. Today, we're going to discuss and review transformations of exponential functions and how these formulas apply to the real world. By the end of this unit, you will be able to read exponential functions and graph them in order to answer word problems. You will also be able to design your own correct formula based on information involving exponential growth and decay. I can't wait to get started, so let's get to it. So before we get started, I'd like to first start off with graphing this equation here. So I have y equals 3 times 2. Now 2 is the base. How do we know 2 is the base? We know 2 is the base because this 2 is the thing that's attached to the exponent. So remember the transformations of any function whatsoever. Remember that transformations look like this. Y equals your a value, whatever your function is, and inside of the function you have k, x minus d, and then you have plus c at the end. In this scenario right here, this is the exact same type of things you're dealing with. This is y equals, for any exponential function, you have y equals, your a is out in front. Now your base could be any number for an exponential function, but then you have k, x minus d, and then plus your c at the very end. This is transformations of all my exponential functions. Remember, the base here is 2, so we're going to start off by graphing this exponential function with base 2. But then we will apply all of these transformations. For instance, your a value is 3. If a is 3, you should know what a equals 3 means. A is your vertical stretch or compression. In this case, it's a vertical stretch by a factor of 3. Then you have your k value. Your k value is a quarter. That's what the k value is equal to. However, if k is a quarter, you should know that's a horizontal stretch by a factor of 4. Okay? And then we also know that we have this d over here, and we should know that if d is equal to 6, positive 6, that's a shift to the right by 6. Okay? And then the last term that we have here is that c is equal to negative 5. So c is equal to negative 5. We know that that is a shift downward by 5. Okay, so we're going to graph this thing using transformations and tables of values. So in order to start this off, if I want this to be my final answer, I'm going to start by graphing the base graph here. In this case, it is y equals, and the base is 2. So y equals 2 to the power of x. That is what I will start with. So how do we graph y equals 2 to the power of x? Well, we can substitute in values for x, negative 2, negative 1, 0, 1, and 2. We know, luckily, how to deal with negative exponents. Okay, I'll start over here, though. When I plug in a 0 into this formula, I get 2 to the power of 0, which is 1. I get 2 to the power of 1, which is 2, and 2 squared is 4. On the other side of this, 2 to the negative 1, remember, you have to know what this is equal to using your exponent rules, but that is 1 over 2 to the power of 1. And over here, 2 to the power of negative 2, if I do that, it's 1 over 2 to the power of positive 2, or 1/4. So that is the first graph, or the base graph for this function. Continuing this, I am now going to apply the next or the first transformation. So the first transformation happens to be a 3 in front of the 2 to the power of x. And that 3 over here is a vertical stretch by a factor of 3. So I am going to take all my previous heights, vertical, and stretch them all by a factor of 3. So since it's a vertical stretch by a factor of 3, my x values stay exactly the same, and I will stretch all these by a factor of 3. A quarter times 3 is 3 quarters. A half times 3 is 3 halves. 1 times 3 is 3. 2 times 3 is 6. And 4 times 3 is 12. So I've vertically stretched all of those things by a factor of 3. Then my next transformation that I see, because I'm going to read from left to right, I have y equals, I took care of the 3, and now the next thing I'm going to take care of is this quarter being multiplied by the x. Now I know that this quarter, your k is a quarter, that is a horizontal stretch by a factor of 4. So if you're stretching everything horizontally by a factor of 4, your y values will stay exactly the same. Those don't change. It is your x values that will get stretched by a factor of a quarter. So I will take all of these x values and I'm going to multiply them all by 4. Negative 2 times 4 is negative 8. Negative 1 times 4 is negative 4. 0 times 4 is 0. 1 times 4 is 4. And 2 times 4 is 8. So I've stretched those horizontally by a factor of a quarter. The next table of values will be for the next transformation. So I took care of the 3. I have taken care of the quarter. And now I'm going to take care of the next thing I see, which is x minus 6. So my d value happens to be 6. That's a shift to the right by 6. So if I was to shift all of those previous points right by 6, my y values, which are my heights, do not change. My horizontal values, I'm going to have to shift these to the right by 6. How do I do that? I add 6 to all these. This is the exact same as any function that we've dealt with so far. If you know these keys, this should actually be very simple, but you just have to be careful. So negative 8 plus 6 is negative 2. Negative 4 plus 6 is 2. 0 plus 6 is 6. 4 plus 6 is 10. And 8 plus 6 is 14. So I took care of shifting everything to the right by 6. Now my last final graph, my last transformation here will be the final graph. I took care of the 3. I took care of the 1/4. I took care of the x minus 6 stuff. And now I'm going to take care of this minus 5. Now this is your c value, and this is a shift downward by 5. So if we're shifting stuff down by 5, my horizontal numbers do not change. And I'm going to shift all of these previous heights down by 5. I'm going to subtract 5 from all of these things. Now, if you have a problem subtracting fractions, you know, this 3/4 minus 5, just use a calculator and use your fraction button. I mean, 3/4 can be written as 0.75. That's fine if you leave it as a decimal. However, if it was a third, you're not going to put that into a decimal. So this is good practice to keep everything as fractions. So I'm going to subtract everything by 5. So 3/4 minus 5 is negative 17/4. 3 halves minus 5 is negative 7 halves. Okay, 3 minus 5 is negative 2. 6 minus 5 is 1. And 12 minus 5 is 7. So this is actually my final graph. And we know that an exponential function goes forever to the left and to the right, unless it was a real life scenario. So I'm going to graph these numbers here. And so I have negative 2. Next time I'm going to figure out how to put graph paper on here. There is a way. So I have negative 2, and this is negative 4.25, I believe. So negative 2, negative 1, 2, 3, 4.25. Got to ballpark that right there. Then I have 2, 1, 2, and 7 halves, which is negative 7 halves, which is negative 1, 2, 3.5, somewhere around there. Then I have 6, negative 2, right about there. And then I have 10, 1, which is right about there. So this is what my graph looks like. Now the 14, 7 is off the page, so I'm just going to do this here. Okay, and this is what it should look like. Now, remember domain and range here. The domain. X is an element of all real numbers because this thing actually goes forever to the left and to the right, unless it's a real life scenario. The range, on the other hand, if you look at the range, y is an element of all real numbers where? Now, remember that for a exponential function, there's always a horizontal asymptote. Horizontal asymptote is a line, a horizontal line, where the graph gets closer and closer to but never touches. No matter how long you draw this, the horizontal asymptote is going to be y equals negative 5. The picture will get closer and closer to negative 5. Remember, that's the key right there. Your C value is negative 5. It gets closer and closer to negative 5 but never touches. Now this one is always above negative 5. So it doesn't hit negative 5 and it's always above. So y is an element of all real numbers where y is greater than negative 5. Not greater than and equal to, just greater than. Let's take a look at page 252, one of the temperature problems, which is number 7. It's a communication problem, but we're actually going to graph this and do everything to do with this and how you would go about graphing this without transformations, actually, because it's a real life example. We don't have to do transformations if we know how to graph this. It says a cup of hot liquid was left to cool in a room whose temperature was 20 degrees Celsius. The temperature changes with time according to the function. T at t equals all this stuff. Use your knowledge of transformations to sketch this function. Explain the meaning of the y-intercept and the asymptote in the context of this problem. Now, this problem is actually really simple because it only asks us for what's the initial temperature and also to graph this thing. So think about this. If we were going to graph this and we have the y-axis as the temperature and we're going to have the x-axis as the time because that's your x and your y, think about what's going actually on with this scenario. There's a cup of hot liquid right now and it's steaming hot. We don't know the initial temperature, but it's steaming hot right now. It comes into this classroom and obviously the longer you leave it in the classroom, the cup of hot liquid is going to lose some of its heat. And eventually, it's not going to be steaming anymore. Actually, eventually, it's going to get closer and closer to whatever the room's temperature is, which is 20. So we have a steaming hot cup of liquid, and it's going to get closer and closer to the room temperature, that's 20. We have to figure out the initial temperature of the hot liquid, and we already know that it's going to end up being close to 20. So basically, this exponential decay problem, or decreasing, has a horizontal asymptote of 20. How do we know? Because the C value is 20. So we know that this cup of hot liquid is going to start at a very, very high temperature. We don't know what that initial temperature is yet. And it's going to decrease closer and closer to that horizontal asymptote of 20 degrees, the room temperature. Now, how are we going to find the actual initial temperature of the hot liquid? That is the key. And the initial temperature of the hot liquid is going to have to be found by plugging in time equals 0, because time equals 0 will tell us what the starting temperature is. So that's what I'm going to do. I'm going to plug in time equals 0 into this formula. And so if I put in a 0 for wherever I see time, I get this. So time equals 0 is going to be 80 times a half to the power of 0, because that will get 0 divided by 30 is 0. And we know that a half to the power of 0 is just 1. So this is going to be 80 times 1 plus 20. So you could see actually that this is 80 plus 20, which is 100. So the initial temperature of this hot liquid is 100. Now, if you did a few of these problems with temperature and you had to graph these, you would start noticing that when you plug in a time equals 0, that kind of gets rid of this stuff over here. It gets rid of this stuff because it ends up being 1. So we know that the initial temperature is always A plus whatever your value of C is. A plus C is 80 plus 20, and that makes this 100. So whenever you're plugging in x equals 0, we know the initial always happens at A plus C, which is 100. So we know that the question asked us about the y-intercept, and the y-intercept, remember, happens when x equals 0 or time equals 0. And so the y-intercept is just telling you what the initial temperature is of this hot liquid, and the initial temperature is 100. Then also it asks you about the horizontal asymptote, and we know that the horizontal asymptote is just what the room temperature is, which is 20 degrees Celsius. Now, I'm going to go further into detail into this question. Let's first take a look at domain and range. So the domain is x is an element of all real numbers. Actually, I shouldn't write x here. I should actually write t for time. So time is an element of all real numbers where time is greater than and equal to 0. Clearly, this is a real life scenario. Time starts at 0 and it goes forever and ever to the right. Then our range. Our range is a little different here because we have y is an element of all real numbers, or temperature is an element of all real numbers, and it's between two numbers. 100 is its highest and 20 is the lowest. It includes 100 but does not include 20. So temperature is greater than 20. I mean, someone could make the argument that it also equals 20, but this is the way exponential function works. So greater than 20, but less than and equal to 100. Now I'm going to get a little more in detail with this by actually graphing this and showing you how to graph this formula with 5 points without using transformations, just based on the actual formula. So this is the actual formula, and let's graph this using 5 points. So how am I going to do that? Well, if I want a table of values for this, and I have time, and I have temperature as a function of time, what values should I be plugging into time? Well, we all know all of these problems, you start off with plugging in time equals 0. Now, again, I think you guys are all pretty smart in understanding that you don't even have to plug in time equals 0, because when you plug in a time equals 0, that's going to make this exponent 0. So you're going to have half to the power of 0. And half to the power of 0 is just 1. So you're going to end up with 80 plus 20, which is 100. Okay, it's always your A plus C is your initial. And so we're going to get 100 for the initial temperature. Then, what increments should I plug in for time? Should I plug in time 1 and then time 2 and then time 3 and then time 4, and that will give me 5 points? Well, I'm not going to do that because that looks a little weird up top here. If I'm plugging in the time equals 1, I mean, that's going to make this exponent a fraction. That's going to be a 1 over 30. I mean, that's very weird to deal with, a 1 over 30, half to the power of 1 over 30 and then multiply by 80. That's going to suck. I am actually not going to do that. See, I'm going to take a look at this formula again. And the number that I should be plugging in for time, if I don't have a calculator and I want to make life easy on myself, the number I should be plugging in for time is fairly simple. I know that this is over 30, right? I know that this is over 30. This half somehow this 30 applies to the half, okay? And so what should I plug in for time? See, if I plug in a 1, that's going to be really weird if I don't have a calculator. If I plug in a 2, also going to be weird. All these things are going to be pretty weird if I start plugging in 1, 2, 3, and 4. But if I plug in the number 30, right? If I plug in the number 30, notice what happens. If I'm plugging in 30, that makes this nice. I can actually do this without a calculator because 30 over 30 is just 1. And so what I'm going to end up with is I have 80 times a half to the power of 1 is just a half, and then plus 20. So all I'm doing is at 30 minutes later, 80 is being multiplied by a half once. So that's 40 plus 20. Okay, so at time 30, I applied the half to the 80 once, and so I end up with a 60 degrees Celsius. That's plugging in 30. So then I should be plugging in increments of 30 into this formula, because if I plug in increments of 30, I'm going to get a whole number as my exponent. So I'm going to plug in a 60, then I'm going to plug in a 90, and then I'm going to plug in 120. So the next number, if I plug in a 60, notice what happens when you plug in a 60. This is going to be 60 divided by 30, which will make this 2. Of course, I don't need a calculator to do this because this will be 80, and then half to the power of 2 is half times a half, which is a quarter. And then a quarter times 80, I'm going to get a quarter times 80, which is 20. And so 20 plus 20 is 40. So this is 40. Now I'm going to continue doing this. I'll let you figure it out in a couple minutes, but I'll give you the solutions for 90 and 120. So you should have got that when you plug in 90, you get 30 degrees, and when you plug in 120 minutes later, you get 25 degrees. Now let's graph this. So I'm going to graph this using the graph I've made over here, where the x-axis is time, y-axis is temperature. And if I graph this in red, I got 0, 100 as my first point. I have 30, 60 as my second point. Notice that my y values go up by increments of 10. My x values, I made them go up by increments of 30 already. That's why I've labeled everything. I have 60, 40 right here. I have 90, 30 right about here. And I also have 120, 25 right about there. Okay, it's also very important for you to label the horizontal asymptote with the ruler. Okay, so that horizontal asymptote indicates that it gets closer and closer but never touches. And then if I connect the points as best as I can and make it go closer and closer to the horizontal asymptote of y equals, actually the horizontal asymptote is temperature equals 20, right? And the initial is 100. So that is a drawing of this with 5 points and without using transformations, actually plugging in the correct types of values here so that you can do this problem without a calculator, and that is all because of the bottom number of that fraction of the exponent. It indicated that I should go up by 30s so that I'm able to do this math without a calculator. Let's move on. Let's take a look at page 262, number 6. It's a knowledge question. It says, a species of bacteria has a population of 500 at noon. It doubles every 10 hours. The function that models the growth of this population, P, at any hour t, is given by this formula here. Now, they give you the formula. Eventually, we're going to come up with these formulas on our own. But it asks you why the exponent is t over 10, why is the base 2, why is the multiplier 500, etc. Let's take a look at coming up with a table of values for this function so we can talk about exactly what is going on. As with the previous problem, the first thing that you should understand, what should we plug in? Let's get 5 points over here without using transformations. this is a real life problem. So clearly there is an initial population of this species of bacteria. How do you find the initial population? Well, you plug in time equals 0. Now, I don't really have to plug in time equals 0 because we should all know what happens when you plug in a 0 into this formula. When you plug in a 0 into this formula, all that's going to happen is that the exponent is going to be 0 divided by 10, which is 0. And basically, when any exponent is 0, 2 to the power of 0 is just a 1. So you could see that the initial population of bacteria is 500. Remember with the last problem, how do you find initial just by looking at the formula? The initial is always A plus C. My A value is 500 and my C value is 0, okay? It's plus nothing at the end. So when I plug in time equals 0, I have an initial population of bacteria at 500. So we should be able to look at this formula and actually come up with that immediately. Then you should be asking yourself, what increments for t should you plug into this formula? If you don't have a calculator and you want nice numbers as your answers, I mean, what you should plug in for t is not a 1 or a 2 or a 3, because clearly when you look at this, we do not want our exponent to be something messed up like this, because we want to be able to do this without a calculator. So what I'm going to plug in is time 10. If I go up by increments of 10, remember it even says that this population doubles every 10 minutes. So if I plug in a 10, what should happen after 10 minutes is that this formula or this population should double. After 10 minutes, we should have 1,000 of these bacteria. Let's take a look if that happens in our formula. So if I plug in a 10, what happens is 10 divided by 10 for the exponent is 1. And 2 to the power of 1 is just 2. So when I plug in a 10, I get 1,000, of course. Of course, it has to work out. How about if I plug in a 20? Because I'm going to plug in increments of 10. And so if I plug in a 20, what's going to happen to this exponent right here? This is going to be 20 divided by 10, which is 2. So when I plug in a 20, I get 2 squared, which is 4. And then obviously 500 times 4 is 2,000. So that looks great. See, after another 10 minutes, this thing doubled to become 2,000. I mean, you can carry this on, but you should understand that after every 10 minutes, the previous number is doubled. That's what exponential functions are. Exponential functions, as your time is going up by the same increments, in this case 10, there is what is called a common ratio that occurs to those numbers. And the common ratio in this case is 2, doubling, which is exactly what this question was talking about, doubling every 10 minutes. So, or every 10 hours, my apologies. So this is what the table of values looks like. And of course, you can also graph this thing. But let's answer all of the questions here. Question A asks us, why is this exponent t over 10? Well, the reason why it's t over 10 is because the doubling, okay, so it doubles, the doubling happens every 10 minutes, okay? It's happening per 10 minutes. Every 10-minute increment, that doubling is happening. Question B says, why is the base 2? Well, the base is 2 because the bacteria doubles. That's what's happening to the bacteria. Why is the multiplier 500 in question C? Well, the multiplier is 500 because that is the initial amount of bacteria that is there. Now, let's take a look at question D. Okay, question D is asking us, determine the population at midnight. So at midnight, we know that at midnight, the time on the clock will say 12 a.m. Okay? And that's very important because this table of values here has nothing to do with the time on the clock. This table of values speaks about how many hours pass since the beginning. Now, if you take a look at the question, it says a species of bacteria begins with 500 at noon. So on the clock, okay, if you had another thing on the clock here, this is, the initial is 12 p.m. on the clock. If you want to know at midnight, what we're going to look at is 12 hours later. Okay, 12 hours later to become 12 a.m., midnight. So we're taking a look at what should this number be. It's somewhere between 1,000 and 2,000, but all you really have to do is plug in 12 hours later into this formula to figure out 12 hours later into this formula to figure out what the population is at that exact time. Now, question E, you got to be careful on question E. Question E says determine the population at noon of the next day. Well, noon the next day is another 12 hours later. Okay, noon the next day is 24 hours. 24 hours after the initial time. So noon the next day, I would have to plug in a 24, not a 12, but a 24 into the formula because the formula deals with how many hours pass by. So, of course, how do we actually do this on our calculator? Some people may ask. So when I go to plug this in into my calculator, I mean, you could just do 24 divided by 10, which is 2.4. And you could actually plug this in. You could plug in 2 to the power of 2.4 in your calculator first. Once you get 2 to the power of 24 on your calculator, multiply it by 500, and you get 2,639. I know there's a decimal associated with, but that is how many bacteria, whole bacteria, there are at that moment. Now, question F is a very, very important question in this unit. So the question, I rewrote all of this, but the question says, determine the time at which the population exceeds 2,000. Now, I mean, this is a very easy question to answer, and that's because this is a knowledge question. But I'm going to do this as if this were not a knowledge question, and it's a little harder question from the other thinking problems of this unit. Now, we can see right there when it does exceed 2,000. I mean, you could see it's 20 hours later. And so you could just add 20 hours to 12 p.m. Okay, so if you add 20 hours to 12 p.m., you can use your fingers, count 20 hours from there, but you know 12 hours later will be midnight, and plus another 8 hours will be at 8 a.m. the next morning. Okay, so how do we actually figure this out mathematically? Because this was a nice number, 2,000. But let's do this question as if they were asking us and showing how we get this mathematically. So what I'm going to do is I'm actually going to rewrite the formula, and the formula looks like this, okay? And if I were to find out time when the population is 2,000. Let's plug in 2,000 in for population. So if they tell me that population is 2,000, how do I solve this when I plug in a 2,000 here? I'll show you how to solve it. There are two ways actually. One of the ways will just be sort of like a guess and check, but we want to try to avoid guess and check. So I'm going to actually show you how to use one of the buttons on your calculator. So the first thing I'm going to actually do here is divide both sides by the 500. Okay, so divide both sides by 500. So I end up with, that cancels each other out. So this is 2 to the power of t over 10. And when I do 2,000 divided by 500, I get the answer of 4. Now, This may confuse people when they see this line right here. How do I solve this if I have this line here? Well, there are a couple of ways. Please, this is not the same as 2 times t, okay? So no, you cannot get rid of this 2 over here. You can't get rid of that 2 by dividing both sides by 2, okay? Obviously, if you divide both sides by 2 here, you get t equals 2, if this was the problem. But if you have 2 to the power of t equals 4, you cannot divide both sides by 2 because this is not the opposite operation of this exponent. You could divide here by 2 because this is 2 multiplied by t. So the opposite operation is divide by 2. This is 2 to the power of t. So you cannot divide by 2 in order to get rid of this. So the question remains, how do you do this? Well, I'm going to show you 2 ways of solving this line right here. 2 ways. One of the ways happens only once in a while, okay? How do you solve that? Well, you solve that, you can actually rewrite this side of the equation. See, this side of the equation is 2 to the power of t over 10. But this side of the equation, I can rewrite that as 2 to the power of 2. 2 squared is the same as writing 4. In which case, if this side is equal to this side, I mean, both bases are 2 now, that means that both exponents also have to be equal. So if I can rewrite both of them with the same base, that 2 is the same as t over 10. I mean, this doesn't always happen because you can't always rewrite that 4 with the same base. It may be a different problem. In which case, cross multiply the 10 and you get time equals 20. So that is one way of doing it. But how do you do it so it works out every single time? And that's what I'm going to show you. I'm going to show you this thing called logs. And you don't know what logs are, but I can show you a little bit of trick on logs right now. So it's extremely, extremely important to get to this section of the video to figure out how to use logs to solve for exponents. So we don't know anything about logs yet, and you will next year. But if you want to solve for logs, you want to use logs to solve for an exponent, this is how you do it. You have to know this rule right here. If you are taking the log of any base to the exponent of any x or any exponent, it is the exact same as writing that exponent then log of the base. Why is this important? So this is a very important rule. Now you can explain this to yourself next year when you know how to graph logs, but you can find and locate the log button on your calculator, and let's just try this with any 2 numbers. Like if I were to do log of 2 to the power of 4, for instance, I mean, we know that 2 to the power of 4 is 2 times 2 times 2 times 2. We know that that's 16. So if I took log of 16, it should be the exact same as doing, now let's take a look at, remember, this rule here says that you write the 4 out in front and then log of the base 2. So if you do log of 16, it's the same number as 4 times log 2. What logs do, and you could try this with another, any other 2 numbers. For instance, log of 3 squared, which is log of 9, is the same as 2 times the log of 3. Try that out. You can do this multiple times, and every single time it works. Now, why? That's not an explanation for why it works, okay? The graph next year will show you more about that. But basically logs get rid of exponents, okay? So logs get rid of exponents. Okay, so logs will get rid of exponents for you. So why is that helpful? It's helpful because even though you were able to do 6f without this, In other word problems, you're not going to be able to do this. So what do? If you have a scenario like this and you are trying to solve, you're solving for the exponent, okay? So the exponent is what you're trying to solve for. You're going to use logs. So how do you use logs? Well, logs, you just take whatever you do to one side, you have to do to the other side. So in this case, how do you use logs? Well, if I took the log of this side, I just have to make sure I also do the same to this side, whatever log is. So I'm taking the log of both sides. Now, how does that help me? It helps me because on this side, I'll just keep log of 4. But on this side, remember that logs get rid of exponents. This side over here can be rewritten as the exponent, t over 10, in front of the log 2. So now, in order to solve this, I can actually mathematically, algebraically solve this because none of this is our exponents anymore. So I can actually divide out, this is actually t over 10 times log of 2. So if I wanted to bring log of 2 to the other side, I would, instead of multiplication, it would be division. So I'm going to divide out the log of 2 from both sides. Okay, so bringing log of 2 to the other side, it would be division. And so now I end up with this. I end up with t over 10 is equal to log of 4 divided by log of 2. And when I do that on my calculator, log of 4 divided by log of 2 actually happens to be 2 by a weird coincidence. Anyways, continuing this is t over 10. If I cross multiply the 10, I get t equals 20, okay? Now this question you could have done without logs, but I'm showing you how to do logs so that when we get to the next questions, you're able to do them.
We interrupt this program to bring you... What?
Sure you want to ball with the team.
When you're running around hitting people and making plays, and that's just something that I just loved. It spoke to like this other side of me. I love math because if you ask yourself what language describes the world we live in a quantitative way, the only answer is mathematics.
So on page 263, number 11, it says a population of yeast cells can double in as little as 1 hour. Assume initial population of 80 cells. Okay, so we have population, total population in terms of time. At time 0, what this sentence says is that there are 80 cells. And it also says that it can double in as little as 1 hour. So every hour that this goes up by, and it's per hour, this is going to double. So 80 times 2 is 160. That times 2 is 320. 320 times 2 is 640, and so forth. 640 times 2 is 1280. So it's doubling per hour though, per hour. It's not every 10 minutes like in our last problem, every 10 hours. It's per hour. So I'd like to skip ahead and actually write out the formula for this scenario. Okay, and we know that the formula for all of these scenarios is y equals a some base to the power of time over and then n. And what is n? N is the growth rate period. So if it's doubling per hour, then n would be 1. If it was doubling every 10 hours, then n would be 10, and so forth. In this case, the population as a function of time is equal to, now A is always the initial population. In this case, the initial population is 80. B is always the common ratio. And we know that the common ratio is 2. So I'm going to put a 2 because it is doubling. And it's to the power of t over 1 because it's per hour that this occurs. So I'm obviously not going to write the 1 on the bottom here. I'll just leave it like this. So this would be the population formula at any given time. It asks us about the growth rate. The growth rate we can get from the common ratio. Now, let me just make an analogy over here. If there was no growth whatsoever, so if this question had no growth, if you started with 80 and there was no growth, all right? So after each hour, there was not any growth, no growth, okay? If there was no growth, the next, I guess, minute or whatever this question is, hour, you would still have 80. And then after that, you would still have 80. And after that, you would still have 80. Meaning that the common ratio is 1. So if there is no growth whatsoever, this common ratio is 1. However, that's not the case. Obviously, it's doubling. So the common ratio is 2. So what is the growth rate? Remember, if there's no growth rate, the common ratio is 1. This is more than 1, clearly. How much more than 1? That's, I guess, 1 more than 1. So that is an increase of 1, all right? And as a percentage, a 1 as a percentage is equal to 100%. So there's actually a 100% increase, not a 200% increase. This is 1 more than no growth. So it's a 100% increase. Then there's a few questions here. Of course, question C says use your equation to determine the population after 6 hours. So all you're going to do is plug in a 6. And whatever the answer is, that's what you're going to write down as your final answer. If I wanted to do this in one shot, I'm going to make sure I take care of 2 to the power of 6 first. So I'll do 2 to the power of 6, then multiply it by 80, because you have to do exponents first. And so I end up with 5,120. The next question asks me to figure out how much is there after 90 minutes. Remember, this formula is in hours. So if you want after 90 minutes, you have to realize that every hour is 60 minutes. So when you take 90 and divide it by 60, this is actually 1.5. So when you plug that in for that question there, you're going to have to plug in the number 1.5 in for the number of hours, and that's for question D. Question E asks, when will the population, approximately how many hours will it take for the population to be 1 million? So that's what I'm going to plug in for population. I'm going to plug in 1 million for population, and that is equal to 80 times 2 to the power of t. And now we're trying to figure out an exponent. So this obviously works off of what I just had shown you with logs. Logs help us solve for exponents. So the first thing I'm going to do is I'm going to get rid of that 80. I'm going to divide both sides by 80 because that is 80 multiplied by 2 to the power of t. So continuing this, that gets rid of the 80 on that side. And now I'm left with 2 to the power of t is equal to 12,500. Now remember how to solve something that looks like this using logs so that you're able to solve it every single time. If I decided to take the log of both sides, so I take the log of 12,500 and I also take the log of 2 to the power of t, remember what log does. So on this side I'm left with log 12,500 equals, and in this side I can write t times the log of 2 because that's what it's equal to. So this is t multiplied by the log of 2 on this side. And so now I can get rid of log of 2 to the other side because Since this is multiplication, if I bring log of 2 to the other side, it will become division. So I have log of 12,500 divided by log of 2. And when I complete this problem, I'm going to get that t is equal to approximately 13.6 hours. Now, I'm not sure if the back of the book rounds that to the nearest hour, but if I wanted to round that to the nearest minute, just understand what that means. It means 13 hours, okay? And it doesn't mean 60 minutes, okay? It means 13 hours, and I'm going to actually take that 0.6 and multiply it by 60, because this 0.6 is in hours. To convert back to minutes, I'm going to have to multiply by 60. And when I do that, I get 36 minutes. So it's actually 13 hours and 36 minutes if it wanted this to the nearest minute. Okay? And that would be question 11. Well, my time for part 1 of this segment on exponential functions has come to an end. Hopefully this video was helpful. Be sure to tune into part 2 as we will discover more exponential growth and decay word problems. I'm the math coach saying, see you next time, and thanks for watching.